Is YouTube ready?
Yeah, we're ready. Is it because it gets to a certain point?
Hello, everyone. Thanks for being here. Good afternoon. We are having the flash talks here today for our third and final prospective students visit. There are going to be 4 talks. First is going to be by Stephanie Henderson, Dr. Steph Henderson, who some of you might have met during the day today. And it's going to be very brief and very informal talks. So feel free to ask questions if you have any questions. Just a reminder, they're usually 10 to 12 minutes talk. So try to keep it short. It's fine if it doesn't because we only have 4 speakers today. And I'll hand it over to you, Steph.
All right, thank you so much, Rudra. Can everybody hear me? Okay. Okay, great. Thank you for the reminder. We are really good at talking. Faculty can just keep going, so we will still have to be careful. So my voice is kind of going up too, so I apologize for that. So I wanted to tell you a little bit about my research group. We're the subseasonal to seasonal variability group. That's kind of what I tend to call us because those are the time scales that our research tends to be at. The way that I'm going to kind of approach this short presentation of mine is I was going to give a little bit of background about the kind of relevant phenomena of the projects that I'm going to highlight that are kind of ongoing in my research group. So these are kind of the 3 topics that I'm going to kind of go over. It's kind of a nice summary of the kind of time scales that my research group deals with. Part of what we do is we look at tropical variability and its interactions. So what you see here is sea surface temperatures in the contours and diabatic heating in the shading. And this is a time versus longitude plot. So this is taking all of the tropical latitudes and averaging them together. So when you see, for example, here we have El Nino Southern Oscillation. This is during a La Nina event. You can see that throughout the entire 90-day period in this figure, the El Nino kind of, the La Nina event changes in amplitude, but it's fairly stationary, right? It stays kind of in the same place. That's quite different from the Madden-Julian Oscillation, or the MJO, where you can see that its location is changing as we move forward in time, right? This is an eastward propagation. The MJO is an eastward propagating system, whereas ENSO tends to be fairly stationary. So one of the things that we do in my research group is we examine how these 2 phenomena interact with each other, other phenomena that I'm not mentioning here, but I'll highlight a little bit later. One of the things that really interests me and that people have worked on in my group is tropical phenomena like the MJO and like ENSO. They force what's known as teleconnection patterns, which you see here in this figure. We examine teleconnection patterns and what impacts they have. So this is during an MJO event, right? So now here we're not averaging all the tropical latitudes, so you can see in this case, the MJO, which is an eastward propagating system, has increased precipitation over the eastern Indian Ocean and suppressed precipitation here in the yellow in the western Pacific. And MJO forces these really large-scale waves known as Rossby waves. And that's what you see in the contours up here. So that's looking at geopotential height anomalies, which are directly related to pressure anomalies. So you can see this kind of like high, low, high, you get this wave train that propagates over the North Pacific and over North America. And that's going to significantly influence the weather that we experience over the US, for example. ENSO, El Nino and La Nina also force these teleconnection patterns. So part of what we do is examine how these teleconnection patterns interact and how that changes any downstream impacts. Lastly, something else that I'll be highlighting here is atmospheric blocking. So I do work that's entirely in the tropics, and work that's entirely in the mid-latitudes, as well as some that connects the two. I can't stay in one place. But it all kind of has this kind of time scale theme to it. So atmospheric blocking events, they're really important because they're associated with weather extremes. So this is an example of a block over the North Atlantic. You can see the US over here on the left of the image, Europe on the right here's Greenland. And this is a blocked flow characterized by this kind of really persistent high pressure system. So you can see the high, this is known as an omega block because it looks kind of like the Greek letter omega. And these patterns can persist up to weeks at a time in different regions. Because of that, you end up with persistent impacts associated with them, and that's what leads to those extremes, right? So for example, you can actually see a really nice image here of this cyclone that's getting rerouted. So it'll block the flow, right? Hence the name, and it'll reroute storms. Whereas normally, if you had nice zonal conditions, you would be able to go straight into Europe. So that you can have impacts on precipitation where storms hit, for example. This can lead, depending on where the block is and its characteristics, you can end up with regions getting a lot of precipitation, and that can lead to flooding, or regions that don't get much precipitation, and you can end up with drought. You can also get, for example, in the wintertime, due to cold air advection that is persistent and kind of continuous here, you can get these like long-lasting cold snaps associated with blocking events. In the summertime, you can get heat waves because this high pressure system is just sitting there. You get a lot of subsidence and really hot and dry conditions. So this is kind of some examples of what we do in my group. And what I'm going to do next is just kind of highlight some of the projects that we're doing as they relate to kind of those topics. So this is some work that my PhD student Grant is currently doing. In this project, we are looking at blocking events that impact North America. This includes understanding them as well as examining the impacts associated with them. So right now he is focusing on blocks that exist over the Northeast Pacific. So in this image here, you can see North America in all of these images. And we're defining blocks using two different indices, and that's what these columns are. If you look at the very top and focus on the black contours, that's geopotential height. What we're looking at here is two different blocking types. Here you can see an anticyclonic anomaly, so that's that blocking high pressure region. And below that we have a minimum in the geopotential height. This is known as a dipole block. And again, this, by definition, will persist for at least 5 days. What you see in the colors are the temperature anomalies associated with them, right? So you can get really high temperatures over regions like Alaska, northern Canada, and then a lot of cold air advection over regions over the US. This is a different type of block. So this is defined just using a geopotential height anomaly. So this is just looking for a high pressure region. This is searching for cases where something like omega blocks would be captured better by this type of index, for example. And you can see that the impacts can be fairly similar associated with the high pressure region, but they do tend to be a little bit different. And I won't go into too much detail with that, but you can see the temperature impacts there. Importantly, they have a strong impact on precipitation, which is what you see in the color shading here in the middle. So one of the things we see with dipole blocking here is increased precipitation in Western California that's associated with atmospheric rivers, right? So high moisture transport, which is what this is showing here in the bottom. This is moisture transport in the arrows, and the colors is showing water vapor. And you can see that this is increased water vapor transport that's hitting California, and that's tied to atmospheric rivers. You see decreased precipitation along regions of Western Canada. So again, you're think about these patterns persisting for at least 5 days, right? So that's a long time where you're getting a lot of precipitation and high impacts in regions like California, or not getting precipitation at all, but you're getting a lot of cold air advection associated with the anticyclone. And then you get increased precipitation along Alaska. That's a little bit different here, right? Here we actually don't see the atmospheric river signal with the other type of blocks. So this is just kind of an example of some of the work that Grant is doing. Oh, wrong keyboard. So to highlight a different project, this is a project that my student Juliana Hara was working on until she finished her master's, but we're continuing that project as a collaboration with John Albers, who is a research scientist at NOAA-PSL. This is looking at the lots of oscillations here, lots of acronyms. The relationship between 3 phenomena that exist in the tropics. So now this is a project that's fully entirely in the tropics. We have QBO, ENSO, and MJO. And the idea is trying to separate and understand their relationship using a tool that I use known as linear inverse model, which is it's a statistical modeling technique. I say I got the 2-minute warning. So if you have any questions, you feel free to ask me later. But long story short, one of the things you can do with linear inverse modeling is separate components. So what's internal to the stratosphere versus what actually communicates with the troposphere and the sea surface temperatures. So you can actually use statistics to isolate processes and better understand how different forms of variability communicate with each other. The last one that I'll just talk about super fast, this is kind of getting at the idea of impacts of MJO teleconnections. This is a project that's a collaboration with Andrew Winters, who was John Martin's PhD student back in the day, and I was faculty at CU, looking at forecast errors in jet position and the role of teleconnections associated with that. So essentially what we see, this is during MJO phases 3 and 4. This is when MJO precipitation is over the East Indian Ocean and Maritime Continent region, right, because remember MJO propagates eastward, and also separated by El Nino versus La Nina. So what we see is these negative numbers means improved forecasts. So we have better forecasts of the North Pacific jet during La Nina versus El Nino. And part of the reason with that has to do with how the teleconnection patterns of ENSO and the MJO interact with each other. So during La Nina, you get what's known as constructive interference, which means both the MJO waves and the La Nina waves both result in this is zonal wind, but both result in an anticyclonic anomaly over the North Pacific. So they both act to provide kind of a similar response to the jet, and that gives us additional forecasting ability, unlike El Nino, where we don't see much difference in the zonal wind. So anyways, I'll stop here so that we have time for everybody else. But thank you, everybody, and I hope that little super fast preview was helpful. And I'll take any questions. I think we have some time for questions. So any quick questions? Does anybody have any questions?
I do. Is there any significance to the Atlantic Basin tripole?
Yeah, that's a good question. So I mean, in this project, we're fully focused on the Pacific, but there would be, right? Because this is just, if you were to take all of the La Nina days that have an MJO phases 3 and 4 at the same time, composite them all together, then they're constructively interfering here, right? But this is also saying that this is their impact combined is resulting in these anomalies over the Atlantic. What their impact is, I don't know. That's an interesting question, and I have no idea how that might change, for example, predictability in this region
Yeah.
or anything else, because we're not quite looking at that, but yeah. Any other questions? Okay, all right. Thank you, everybody. I will, on the next speaker come up, Tristan.
McVA.
Did you want the mic?
I'll try without the mic. I think I can
Okay.
probably do it. All right. Okay, so my name is Tristan Lequier. Let me know if you can't hear me, but I can usually project pretty well. I am on the 15th floor in room 1511. You can also, I'm also the director of the Cooperative Institute downstairs, so you can sometimes find me at 241 as well. And those are the three classes that I typically teach or I've taught recently. The main one right now, due to my role as the director, I have a reduced teaching load, so I teach radar and satellite meteorology, 441. I'll talk about that just at the end. So my research mainly focuses on using satellite data to understand aspects of the climate system and try to evaluate how well we're representing those in our climate models and hopefully make some improvements, or at least guide some improvements. My career to this point really kind of owes itself to this train of satellites that is now, just as of December of last year, no longer in existence. But in particular, the CloudSat and Calypso missions that launched in 2006 that filled out this this train of satellites known as the A train were basically what I built my career on. It was trying to understand radar observations and LiDAR observations from space and what that taught us about the role clouds play in the atmosphere. The nice thing about having these 5 satellites together, this is kind of the first time NASA ever really tried to do this. We had a variety of different perspectives, things like measuring precipitation, measuring the cloud top properties, measuring what's in the cloud from the radar and the LiDAR, and measuring aerosol profiles using the LiDAR. Parasol even measured the shape of ice crystals in the atmosphere. We had all of that simultaneously, and so there was a tremendous amount of science that we could do, and are still doing, using all of these observations. Just as one quick example, this is work that I did with a PhD student, Alex Mattis, in a paper in 2017, where we looked at what the radiative effect of various cloud types, very simply categorized in terms of whether the clouds were made of ice, made of liquid, had some combination of liquid or ice together, or were multiple layers of distinct cloud, like an ice cloud above a liquid cloud. And what we wanted to do is try to identify what their impact was on Earth's radiation budget. And so you're looking at maps of the locations of their radiative effects. And we're looking at here in watts per square meter on the annual average, how much they influence the radiation budget at the top of the atmosphere and at the surface. Without going into any details, obviously you see some unique patterns. You see ice clouds warming, liquid clouds tend to be cooling. But the interesting thing, and what was really novel about this work, because we had the radar and the LiDAR, we were able to determine these mixed phase clouds, clouds that had a combination of liquid and ice in, really for the first time, and we were able to diagnose what their impact was on the climate, and we found it was actually quite large. Even though they only make up about 8% of cloud cover, mixed phase clouds actually contributed 20% of the net cloud radiative forcing at both the top of the atmosphere and the surface. So that was kind of an interesting finding. Oh, I don't know why the title's a different color here, but it might have been just using the widescreen thing. On a related topic, this is now focusing on a very specific type of clouds, looking at the radiative influence of deep convective clouds. This may be, one of the kinds of views that you may be used to, looking at geostationary satellite imagery, which provides really nice information and great visuals on what's going on at the top of the cloud. But as I said before, these active sensors, this radar and the LiDAR in space, allows us to go a step further and look at what's going on inside the cloud. And so this was recent work by Juliette Paluski and my group, where we used the CloudSat observations to identify all convective objects, basically convective areas that CloudSat observed. Here are 2 examples. These are height latitude cross sections of radar reflectivity. This is the corresponding view from the top. And so we're looking at what's going on inside the cloud, how tall the cloud is actually getting, where the precipitation is falling within the cloud, how big the convective area is versus the anvil area of the cloud. Those sorts of things that you can't get by just looking at the view from the top. The two different images here, this is just an isolated convective system over Africa. This is another one in the South China Sea, a much larger complex of convection, probably associated with a much bigger synoptic scale system. Notice the scale here, 25 degrees of latitude on the this large multi-core convection system versus 0.2 degrees of latitude for the isolated system. And so what we've been doing is using these observations to understand how the radiative effects of these clouds differ as a function of how intense they are and whether they have one core or multiple cores. And also trying to relate that to the rainfall that's falling from them. More recently, my research has shifted toward the polar regions and trying to understand, first of all, what is the balance of incoming solar energy and outgoing long-wave energy in the polar regions. This is a diagram that I put together with Marion Maitling, who I think I saw in the room somewhere, yeah, we're basically under this NASA Energy and Water Cycle study, compositing the best observations we have with our uncertainties of all of the energy fluxes in both polar regions, and from that trying to understand how much energy needs to be transported from the equator to the pole in both hemispheres. And then from that, we're now trying to, with a new satellite mission that hopefully will launch here in a couple of months, trying to understand what the actual spectrum of that emitted energy is. So from the previous slide, let me just go back. There are some fairly large uncertainties on this thermal portion of the spectrum. These uncertainties are even larger when you look at models, climate models, or even reanalyses. We're trying to nail down that uncertainty and understand what processes are impacting the emitted energy in the polar region. So this is really my main focus right now, trying to get these two CubeSats called this Polar Radiant Energy and the Far Infrared Experiment, get those launched. They're going to measure the complete Planck function at the top of Earth's atmosphere. We've measured this Planck function for every planet in the solar system, but we haven't measured it for our own yet. It's because it's actually much harder to look at yourself than it is to just look out at somebody else, right? So we've looked at all the other planets. Now we're going to launch some satellites that will look at Earth. And through this mapping of the entire emission spectrum, we're going to try to understand what processes, what gases in the atmosphere, what clouds affect different portions of the spectrum, and hopefully improve the representation of those processes in climate models. The reason we're launching two CubeSats, well, first of all, because we're using CubeSats, each satellite is actually much less expensive, maybe almost 100 times less expensive than a typical mission, a conventional mission. But we're launching two of them so that we can overpass the same areas on the surface of the Earth within 12 hours of each other. We want a variety of different times. We want to be able to understand what the various processes occurring on the surface, things like melting of the ice sheet or a water vapor intrusion into the Arctic. What do those processes do in terms of modifying the emission spectrum of the polar regions? And so by having two CubeSats, we'll get intersections between the CubeSats and try to understand this process level influence on the energy budget. Okay, that leads me to my other role. I have just one slide on this, but hopefully you've heard a little something about this or already know that AOS is, I think, very fortunate to have the Cooperative Institute for Meteorological Satellite Studies and the Space Science and Engineering Center in the same building. We have the longest record of geostationary satellite measurements in existence. Goes all the way back to the sort of the original GOES-1 era. We also use these observations for a variety of different products, excuse me, to benefit society. Things like cloud cover, identifying fires, looking at volcanic ash, even turbulence now using machine learning techniques. And so the main message here, I'm the director of SIMS. SIMS also supports a number of graduate students in the building. These data are accessible. There are a lot of subject matter experts downstairs that you can talk to if you're interested in using satellite data in your research. And like I said, we don't have to download the data. every time you want to use new data, it's pretty much all in residence here in the building. So this is a really nice complementary activity we have going on in our building. And I'll conclude with just again, this plug for what I teach. If you come in the fall and if you are not yet an expert in radar and satellite meteorology, take my 441 class. I have a lot of graduate students and professional master students that sit in on that class as well. And so we'll get to learn, this is the radar and the satellite perspective, both the visible and infrared of Hurricane Michael, as it probably the strongest storm that's ever hit the U.S. Mainland, hitting the panhandle of Florida here. You'll get to learn how to interpret these observations and hopefully, again, improve the forecast for the general public. So I'm also happy to answer any questions you may have. Yes?
I have a question that I think is an interesting perspective for the students as well, is how long ago did you start thinking about pre-fire? Like, how long is this process from your first thought to launch?
Yeah, that is a good question, and believe it or not, this answer is going to be short compared to, I think, some other missions.
Yeah.
About 10 years ago is when we started the concept. We wrote the proposal. The proposal itself took about a year to put together and actually considerable resources to do. The selection process was 18 months. We got going, I think, early 2019 maybe, and we've been working on building the satellites for about 5.5 years. There are other missions, the Tropical Rainfall Measuring Mission that you know very well, that were conceived of in the late 1980s and took 10 years before they even kind of started building, cutting metal. But these CubeSat programs are a little bit quicker, so even though 10 years sounds like a long time, it's actually a short time in a satellite lifespan. Okay. Next speaker. I guess we don't know who that's going to be until I get out of this.
I think they all
Just
have
hit next.
PowerPoint.
Yeah.
Oh, just go to the next slide? I'm
Yeah,
sorry.
thanks to Virgil.
Yeah, perfect. It's you.
Is me next?
There you go.
This on? No. Can you hear me?
Yep.
Oh, I got the team in the back there. Got your picture up here. Hope that's okay. Welcome to the visiting students. This presentation is with you all in mind and recognizing you're not all from a meteorology background. So I'm keeping this really high level and there's emojis and it's not really as technical, so here we are. This is my Wisconsin group and we work on a wide variety of projects, but you'll see some commonalities in all of them, and I like to call them my adventure squad, even though you never heard me refer to as that, because they've all been put through quite a lot to get the data that they are using for their research. So it's something I'll talk more about. I also still work with a few students at Washington that I advised before I was here. So we have a good team, and you'll see my research ties a lot with the classes I teach. So I teach a grad level physics class that we've started bringing some undergrads in. I've got a mesoscale course that I teach. Field observation, well, it's meteorological measurements, but I call it the field ops class because the time I took it, we went out in the field for most of the semester. I'm also, my main expertise is within radar meteorology, and if someday Tristan doesn't want to teach radar, I'm going to jump in. And I focus a lot on orographic precipitation, meaning precipitation associated with mountains. All right, so what are my overarching questions? Why does it precipitate where it does, when it does, for as long as it does, and at that intensity? It is a really hard question that I'm not going to obviously answer all by myself, but this is the overarching guide that I'm thinking about and all the different smaller scale processes that can dictate these processes. So first, mountains. A lot of my work focuses a lot on the roles that that mountains play, particularly in enhancing precipitation. And that can mean through the microphysical processes, meaning the actual production and conversion of water vapor to precipitation at the ground, or its influence on other mesoscale processes that can change the location of rainfall. And this has come in different forms, from Washington State, where we looked at cold season precipitation, all the way to the subtropics and tropical environments looking at monsoon precipitation. Also the ocean. So more recently, thinking about the environment over the tropical oceans in particular, and how do the environmental conditions of the oceans lead to different ways in which precipitating systems organize, and how those processes are different over tropical oceans than, say, what's happening over the mid-latitudes, particularly in mountainous regions. So how do these storms grow into ones that span on the mesoscale, so more than 100 kilometers in size? And there's a lot of different processes that can contribute to that vary in these different environments. So in emoji form, how do we go from individual clouds, and that's what I refer to as organization, because that means different things to different people, merge. And this can happen in very different ways, at very different rates, and on different scales. And when I talk about different scales, I mean all the way from using a microscope to looking and spanning hundreds of kilometers. So I want to highlight, Anthony isn't here, he's actually presenting at the European Hail Workshop, his recent work where he developed a new technique to understand what particles are trapped within hailstones. Because ultimately, if we want to know how hail forms, we need to know more information about the type of particles that water and ice nucleate upon. And so there's been different ways throughout the history of hail research that melts the hailstone and looks at its chemical composition. But he's actually been able to find ways to preserve individual particles and get a lot of information about their chemical composition. So we've been looking at this over Argentina. This is a result of a citizen science program where people can call and they pick up the hailstones. And Anthony's been able to analyze many of them under a microscope. But also, I'm focusing a lot on Argentina. A lot of my work is actually outside the US, interestingly enough. So here's the mountain scale again. And one of the really interesting things about Argentina is there's a small mountain range east of the Andes that it's like putting a mountain range kind of more in like eastern Kansas or something, a pretty substantial mountain range that is a global hotspot for not just frequency of convection, but among some of the deepest in the world. So we actually scanned this storm, and it reached 21 kilometers. And so the question is, not only are these deep storms going to produce the large hail, but Argentina is somewhat unique in that a lot of the hail forms within these large systems overnight, over the mountains. And so one of the things my group has learned is we've looked very carefully at how the mountains modify the local wind shear environment and how that leads to a growth of these systems on a scale that's much faster than what we see in the middle of the US. So we're starting to learn quite a bit from this. This was from a field campaign in late 2018, early 2019, that we're getting some really interesting results on. And the tool that binds all this together is thinking about using radar. And so Tristan highlighted his satellite-based perspective. I focus primarily on ground-based, but it's obviously a useful tool also to compare with what we see from satellite. So we can think about this in terms of a mobile framework. So this is a DAO that now lives at Illinois. There's Illinois folks here that's now called The Farm, which is really clever. But here's an example where we were stationary, planted for a season, looking up the valley and understanding the roles of various microphysical processes, especially highlighting warm rain processes that happen below the melting level and producing enhanced rainfall on the mountains that are predicted just terribly. We do a really poor job, especially in this area of Washington State. So I mentioned I take a global perspective, and one thing I want to highlight is my childhood dream was to run outside and collect data, and so this is what my group does. And so everyone goes out and they understand and feel and recall everything they went through to get those data points. And so I want to highlight that we take a global perspective on this. Most recently, finally getting to fly through some storms, and I'll highlight a little bit of a research, but we really think about this from a global standpoint, where radar is our common tool, ground-based, shipboard, and airborne that our group works out across those platforms. So here's some highlights. I always have to show this one. This was a project completed, supposed to be 2020, pandemic had other plans. So you can talk to Ian about what it's like quarantining for a field campaign and then getting dealing with flooding waters, etc. But this is a place where we get very frequent rainfall, but we were able to have a radar located on the northwest coast of Taiwan, where we now have some statistics of looking at environmental conditions that lead to a wide spectrum of rainfall intensity that we are rarely able to get from other regions because it just rains so dang much in this location. And so we're already starting to learn, surprisingly, Ian has a great paper about how the terrain modifies the Mayu frontal system and whether or not it stays put or moves throughout the location. But we also think about kind of your afternoon intense thunderstorms and the different microphysical processes that lead to very intense rainfall versus the longer duration rainfall that we observed. We had a 6-day rainfall event over the mountains that we're looking at in a lot of detail. I mentioned the Argentina project. I like to show this because for those who are well-versed in severe weather or thinking about radar, our supercell is flipped, thinking about the southern hemisphere, but this is an example of our mobile facilities, like I had mentioned, trying to understand the processes leading to rapid upscale growth. This was a rare case where it stayed an isolated supercell, but it's way less frequent than what we see here in the US. And there's much fewer tornadoes in this region. So we're starting to understand some of the processes that distinguish between the two. This will look familiar to Ben and Giselle. This is an airborne campaign over the eastern tropical Atlantic, where we actually finally, which is hard to get, have really good wind observations near convection. So there's a Doppler wind LiDAR that was flown on the same platform as the convection, and we're starting to really understand not only just the variability of the wind shear and moisture relationships with the precipitating systems over the ocean, but how they're related to some larger scale features like African easterly waves, and that's a big focus that we're diving into. So I have 2 final points. The one I was hesitant to show, but because I'm kind of recruiting some of you potentially for this project, we're waiting for official word of our next goal of really understanding microphysical processes. So I'd like to introduce very briefly snow climb. Yeah, one of the best things about field research is picking acronyms, so that's the whole thing. This is a really heavy slide. The point I want to make is one thing we really struggle with models is ice. Ice is so hard. And one of the challenges of that is we have all these great remote sensing capabilities, but there's a lot of assumptions you have to make about the characteristics of the ice particles, their density, how fast they're falling, etc. What processes control the different densities. There's a lab in Colorado called Storm Peak Lab, some people may be familiar with it, that it pretty much sits in cloud during snow events in the winter. So it's an in-situ, we don't have to go out with the plane now with our in-situ observations. We can sit there and stare at it with different radars at different frequencies to validate some of our retrievals that we have about ice microphysics. So this is looking forward of some things we're really excited about, where I like this graphic that, for those of you who remember Claire Henderson, this is the lead PI of this project. Marion's back there, she's gonna be part of this, where we're really gonna connect the large scale, thinking about the large scale conditions that set up the environment, potentially water vapor content, how mountains can enhance that to enhance supercool cold water, to look at ice processes, but also think about how we sense them remotely. So, not celebrating yet, need an official word, but I just want to highlight as a really exciting thing to look forward to. The final thing I want to leave with, which is the thing I find most valuable, is you can't do any of this without a team. All of this is highly collaborative work, and you can't have an effective team unless you create a space that is safe and inviting for people from a lot of experiences and backgrounds. So a big passion of mine is working on project codes of conducts, active bystander training, working within really diverse and often challenging environments, including internationally, to create a space where more people can be engaged in field work. So I'll end with that. Please email me if you'd like to talk more, and I think I left a minute or so for questions, so thank you. Any questions? Any of the group want to share a field story? They're still here, so we're good. Yeah, Till?
What does snow climb stand for?
God, I knew you were going to ask me that. It is. Mary, can you help me out?
Snow something. No, I don't know.
Climate, Colorado mountain environment. You know you're getting desperate when you're using like the lowercase letters. I did, yeah. Let me get back to you on that. You know, my favorite field campaign name was Relámpago, because you all know what Relámpago means in Spanish and Portuguese, right? It's lightning. But we made it into like the most ridiculous acronym that I'll never remember.
You know, I guess I have a question, Angela, if you don't mind. How do the mountains in Argentina, away from the Andes, if you had to tell me what was the primary thing they change about the otherwise severe storm environment right now, as you understand it, what would it be?
So, oh man, I don't know if I can do this in a minute. This is good practice, see if I can do it succinctly.
Yeah.
There is both a dynamic and thermodynamic influence, but I'd say what we're finding in terms of why they grow quickly. So there's a lot of questions in terms of the roles mountain play.
Yeah.
But in particular of why they grow so rapidly is what we're finding is that the timing of, it's kind of the perfect storm. If you time the mountain slope circulations with the timing of the release of the Cape, which happens very similarly to the US, right? The Andes use a similar approach of subsiding dry air that creates the cavern inversion. But what we need, it's not only just a forcing mechanism, but if you time the South American low-level jet, which forms differently somewhat than the US one, combined with the diurnal circulation, you can orient the wind vectors in such a way that's more aligned to the forcing mechanism, which is often the terrain that allows for a more rapid upscale growth. That is the most short version I can say of what we're working on now, but we're finding that it's playing a big role in orientation of the shear vectors.
And is the difference in tornadoes then a function of it's not ingesting vorticity rich?
Yeah, the low-level shear is weaker.
Yeah, okay. That's interesting too.
So I'm happy to talk to you a little bit more about some of the stuff we're finding on that, but overall low-level shear is weaker.
That's neat. Thanks.
Yeah. Till, you're up.
Sorry, I have my shoelaces on. I'm not just hiding.
Just don't bang your head.
Okay. Well, thank you for the opportunity to talk to you. Welcome to the visiting students. I am thrilled to get the chance to introduce a little bit of what we in our group do. I realized that my title is Ice in the Climate System, and as many of the more senior faculty know, sometimes you shift your interests a little bit, and there's some slides here that don't have anything to do with ice. So I apologize for that. I don't know myself how comfortable I feel with that. So here we go. I've tried to make like a little schematic of what we cover in my group. So my background is quite sort of theoretical, and then I brought in some numerics, and I've always been interested in observations. That is like sort of as close to a non-slide as you get, because that basically covers everything, right? So the biggest part here in the center is climate modeling, because that's sort of like the heart and focus of what we do. And we typically start with something that's sort of quite theoretical, maybe just a partial differential equation. So what I try and do is pick a certain process in the climate system and reduce it to its simplest form, and then try and analyze it analytically or with simple solutions and gain some understanding. And so then you start with something that you can write down and solve mathematically, and then you try and bridge the gaps to global climate models. There's sort of a spectrum of increasing complexity, and you end up with the real world, and you kind of want to, you want to know what's going on here. But if you start with this, that in itself is almost like a black box. So you don't necessarily get a lot of understanding from a very these models have millions of lines of code, right? So just by looking at that output is a little bit like just observing that, right? So we want to build that stepwise. So in this very example, for example, I try to understand the role of sea ice in setting the energy balance at the in the Arctic region. And what I did was I started with a spatial model, where this is sort of my icon for spatial changes, and I added a thermodynamic seasonal model, right? This is like a seasonal cycle. Those existed previously, and then my new contribution was to bring those together and then create a sea ice model that is both spatially varying and seasonally varying, and that sheds some light on the processes. So that is sort of like a typical way of how we try and build understanding. And then we try and bring in some in situ data or satellite data to validate that, to sort of build understanding overall. Another example of what we're working on, and this is, and so you'll see there's like 3 topics here, and I'll give you a 2-minute example for each one of this. I'm really interested also in glaciology, where we try and represent a ice glacier beam as a simple elastic beam with one equation. Then we realize that totally doesn't represent what the real world is, so we make it more complicated, and eventually we get to something that is more representative, and then we work our way back and try and build understanding that way, right? And sort of that iterative approach. And then another thing that I have been getting interested in more recently is, you can't quite see it, ice ecosystem models. So where we're also trying to understand how do the physical components of the system impact, for example, algae blooms in the Arctic. Okay, so let me give you one example of just how we do this type of modeling approach, because this is very relevant, because we just got funded to work on this, and I have a grad student who's unfortunately not here right now, but Clark came up with the best poster, and that's why I'm showing this. So not just the best poster, but also the best title, AMOC, The Circulation Strikes Back. And I took the liberty of replacing the liberty with the burning flame of the NSF. So the idea, and I know it's too small, so please don't worry about the details here. The idea here is that there's a long-standing, ongoing debate of whether the Atlantic overturning circulation is at the danger of shutting down under global warming. And that's to do with the region in the North Atlantic that forms dense water kind of not forming that dense water anymore. And then you have these feedbacks, and then you might end up with a shutdown of the AMOC, which has potential great implications for the Northern Hemisphere climate and global climate. And the thing, if I was to go back to my spectrum on the previous slide, is that global climate models typically don't show such a slowdown. And idealized climate models that only pick out 1 or 2 processes can show a collapse very easily. And there's this long-standing debate of what's right, okay? Are the climate models, the global climate models, just too stable, unrealistically stable? Or are the idealized climate models just unrealistically unstable, okay? And so what Clark is going to do, together with Liz, I did put Liz in here, hello. So we just got funded to test which ones of these models are more likely accurate in predicting a collapse or a non-collapse of the AMOC. And so we're going to like basically try and move along that complexity spectrum in both directions and try and see where the real world most realistically falls. And Clark's recent results that are shown here basically highlight that just from the idealized models, just looking at the idealized models, you might get sort of the mirage of a collapse that doesn't really correspond to a collapse. And there have been some very high-profile papers that have argued that these idealized models, or that even the data, shows signs of a collapse. And here we show that those signs may well be a mirage. And so that a collapse of the AMOC is certainly not guaranteed. Good. That's Clark's awesome poster. Then the second one is more of the glaciological focus, and I'm very excited to talk about this, because this was Nicolas who's been working on this for the last year or so. a very specific question of the wave erosion of ice cliffs. So you can see for this beautiful looking iceberg, there is some very gradual melting happening down here. You can always tell whether it's water melting or surface erosion, because water melting is much smoother than the surface erosion. And so what happens if you have an ice cliff hanging out in water, the wave action will bring a lot of energy and rapid melting to that wave notch. It'll create this type of wave notch, and you can imagine if that notch goes in deeper, the side above it will collapse. And in our current world, where we're very concerned with loss of ice from the Antarctic ice sheet, the relative importance of that process is quite important and quite desired to find that out. So Nicolas has been looking at a very specific process where if you have that ice notch eroding near the water line, the part above it will collapse always because it's exposed to total gravity. The part above the notch will erode pretty fast, whereas the underwater side doesn't erode as much. So is this clear? This is like a glacier flowing into the ocean. Okay, this is the glacier front. Sorry, this is a typical professor thing. I've looked at this for 10 years. I know exactly what's meant, and you might be like, whoa. Okay, so let me take a step back. This is sort of like in a cartoon of what we picture, right? There's crevasses at the top and at the bottom, and there might be predominant erosion near the top, but then less at the bottom. And this part of the ice wants to come up because ice is lighter than water. It wants to rise, so it exerts a buoyant force at the top here. And if you have a crevasse here in the back with some weakness, that whole thing might break off. Okay? And so what we do again is instead, modeling this is quite complicated, but you can turn this to a fairly good approximation into a 1D beam, and you solve that analytically, and you can get an estimate of what's actually going on. And so that's sort of that progression. Yeah, we come up with a concept, we formulate it as easy as we can, as simply as we can in a mathematical model, and then we compare it to observations. So this is a picture of an iceberg near the Ross Ice Shelf. You can see some little flags. It's about, this dimension is about 500 meters long. And what happens, that red line is the same as this. So what happened here was that this piece broke off and then rotated until it reached its hydrostatic equilibrium and then sort of drifted off and froze back into sea ice. So it's like frozen into sea ice. The thing is, nobody's actually ever seen this at the front of the Ross Ice Shelf. This is a figment of my imagination. So I've just given you this whole talk. It's not really a thing. No, we think. No. Okay. We're pretty sure it's a thing because. Okay, so this is the thing. We can measure the surface of the Ross Ice Shelf very accurately from satellites down to almost the centimeter. And what we see at almost all of the Ross Ice Shelf is that the front has this particular shape. It has this, what we call a moat, and then a rampart. This rampart moat shape. And you might be like, oh, this is all totally irrelevant. Let me tell you, the Ross Ice Shelf is the size of Texas. Okay, so this is the biggest piece of floating ice in the whole world. And almost the entire Ross Ice Shelf tips up at the front. And we don't know why. And so the simplest explanation, I think, is that you have like this foot that pushes it up. And so we're writing a grant right now to go there and measure it, which is kind of risky because the ice always collapses, and so you don't want to go too close, because otherwise you perish. But you maybe can go somewhere here and then send like a submarine or something. Right? So we're going to do it indirectly. But it's really cool because we're working on this with some scientists at Lamont at Columbia University, because they have an alternative explanation to what's going on. They think it's because the ice is way colder up here and warmer down here, there's an internal bending gradient, so you don't actually need this ugly foot. You can just have, by the thermal differential, you can have an upward bending that way. And so the idea is now we're going to go to Antarctica and see whether there's a foot or not. That's the idea.
Is that as strong as the buoyancy force?
How does the thermal differential work?
Yeah, that
Can you
seems cool.
explain that again?
Yeah, and so it's cool because so Nicolas we submitted this 2 weeks ago to the cryosphere, and Roger Buck at Lamont submitted, I think on the same day, his alternative explanation.
Does he have wreckage like you do?
He doesn't have this footage, no.
Oh, well?
But his math is kind of maybe nicer. So yeah.
I don't know.
So the idea is because it's way colder here, your viscosity is higher up here than down here, and if you have a viscosity differential, the viscous creep allows for that uplift. That's essentially the process. Okay, so that was just an example. I'm almost done. We are also combining this with experiments in the geoscience cryo wave tank that's in Luc Zuid's cold room, so that we can reproduce this. And yeah, so there's a theory component, lab component, and climate modeling. And one of the engineering students has been working on this and is doing, Anja Walterman is doing amazing work. So that's in collaboration with geosciences and engineering. Okay, I got a little sidetracked by the footloose mechanism, but just in my last minute, I wanted to show briefly my third project that I'm working on with this fantastic former student of mine. He was an undergrad, Connor Lester. We went to the Arctic together to look at how sea ice melt impacts the algal blooms in the Arctic at the beginning of the spring season. And so there's me here and Connor and a couple of students. It was a very great trip. And the reason why we got so excited about this is this very unique data. So this is sea surface temperature, and this is chlorophyll. And what you can see is that exactly where it's cold, these things are sea ice, and there's Svalbard. And this is about 300 kilometers across. And there's the Svalbard archipelago in the Arctic. This is sea ice flows. You can see there's sort of these meanders. And so this depressed sea surface temperature is where you have meltwater coming from the sea ice. The sea ice is melting, and it tracks. You can tell exactly where the meltwater is, right? And what's so striking here is that there's these very clear links between the sea ice meltwater plume and the chlorophyll concentration here. Here, the same thing. And that is not trivial, because typically we associate warmer temperatures with larger growth. And so somehow, in this case, you have colder temperature producing those algal blooms. And what we think is happening in this world, it's very unique, is that the sea ice meltwater is fresh and light, and it sits on top of the ocean, and it stratifies that very top layer. And the chlorophyll particles are passive tracers. So when they are stratified with that meltwater in the top layer, they're more exposed to sunlight, and so they grow better. That is sort of our working hypothesis, leading order hypothesis. And so Connor's been working on writing this into, again, an idealized model that's looking very good, and we can reproduce these patterns really well. So that's another thing. So there we go. Thank you. We have one, yeah?
Is there something different about the meltwaters, what's mixed with it? Like some organic matter from the ice shelf as opposed to the ocean? Could that be another factor?
Yes, it is something that we've looked into, and it looks like in general the sea ice doesn't have that much material typically.
Okay.
So the assumption is that you are, this early in the spring, you're not really nutrient limited. So you're growing fairly quickly,
Yeah.
and the main limitation is the light.
Sunlight, okay.
Is the
Very
sunlight.
interesting.
Yeah. is from what. And you know, we took ice cores, and it is generally quite well known that the ice is fairly particle, like nutrient free.
Yeah.
It's not super rich. There is a complicated relation to under ice algae. There is algae that are under the ice, that grow at the bottom of the ice, and I don't understand quite how they tie in with those open water blooms. Yeah.
Very cool.
Okay. Thank you all for coming.